Okay, this is the continuation of series in Convergence, so section 9.2. So we're going to start with talking about geometric series. So what we learned in class is that a series is the sum of the terms of a sequence. And again, that big capital letter sigma means sum. So geometric means that each time to go from term to term, we're multiplying by r. So we'll have r, then we'll have r squared, then we'll have r cubed, and so on. So we simply take the previous term multiplied by r. So that gives us our series, and this is what it looks like. Or this way, doesn't matter whether you start at 0 or 1. But either way, there's an a, which is some constant, which could be a 1, so you wouldn't be able to see it, and then r, and r is the ratio that we're multiplying by to go term to term. And then because it's a series, we're adding them up. Okay, so this is the sum of the series. So the formula here, which is very important, is that how to determine whether it converges. Because it's very difficult to determine whether a series converges by that definition that we talked about, and that is whether the sequence of partial sums converges. So we are going to learn to match things. So we need to match our series that we have with something that can give us a way to determine whether it converges or not. And we certainly won't be able to tell if they all converge. But if we happen to know if it's geometric, we can definitely tell if it converges. So if it's geometric, we determine what r is. And r, again, is the ratio that you're multiplying by. Well, if you have ratio r, it will diverge if the absolute value of r is greater than or equal to 1. And then if the absolute value of r is between 0 and 1, then it will converge. And not only will it converge, it will specifically converge to this sum. So this sum is very important. Now, I would not memorize it as what they have written, which is a over 1 minus r. I would change that to a1, but I will encourage you to never say a1. I will encourage you to always say, when you see a1 written, as first term. So a1 would always be the first term that I start with, and so you would always just start off by saying the first term. So first term over 1 minus r. So that's how I would learn that formula. Now this partial sum of geometric series we're not going to worry about because we're not going to do that. So don't worry about that one. So this is a geometric series. So they tell you it's geometric. But the way I can see that it's geometric is I can tell that I'm multiplying by 1/5 each time to go to the next term, because of course the top is staying 8, and then you're simply multiplying by 5 on the bottom each time, which means I'm multiplying by 1/5. So a1 means the first term. So the first term is 8. So like I said, when you see a sub 1, like I would even read this problem, find the first term. I wouldn't even say find a1. And then what is r? Well, r is going to be what I'm multiplying by to go term to term of the sequence, and then I'm adding them all up, and that's what makes it a series. So r is 1/5. Then it says write an explicit rule for a sub n. So that means write this basically in summation notation. Now, I almost always start with 1 and not 0, but you can start with either one. The key is just making sure that after you write down your formula that it matches up. So we know that we have an r of 1/5, and we know it's raised to a power. Well, if I start with n, if I say that the power is 1, then that's not going to work, because then I'll have 1/5 to the first, but we know the first term is 8. So we're going to do n minus 1, so that when we plug in 1, we'll get a power of 1 minus 1, which is 0. So that's going to be a 1. And then, of course, we have to have the 8. That's the first term. So there is your explicit rule for a sub n. You'll get better and better and better at these as we go. So the fourth partial sum, S4. So that means to literally add up those four terms that are up there. Because remember, S4 means the sum of the first four terms. So we want to add these four terms up. And so we want to get, this is where we want to be smart so that we don't spend a whole bunch of time. We can see clearly that the common denominator is 125. So we know we multiply by 5 here, which means 5 there. Here we've got to do by 5 twice, which is 25. And then here we'll have to multiply by 125. Make sure you write it on top and bottom because we don't want to do anything that's incorrect. So we have to show top and bottom. Now this is not as hard as it might seem to do this arithmetic, but you're going to be loaded with arithmetic as we do series. So really, really important to get really good at it. You can see that we clearly made a common denominator of 125. So all we have to do is figure out what do we have in the top. Well, 8 times 125, so a quick way to do that multiplication in your head is 8 times 100. So that's 800 plus 8 times 25. Well, 8 times 25 would be, if you had money, you have 8 quarters, you have $2. So that's 200 plus the 100, that's 1200. This is 200 because we just talked about that. So now we're at 1400. That's 40. So that's 1440, or sorry, 1200, 48. Sorry, this was 800 plus 200, which was 1000, sorry, plus 200 in the second one, and then 40, and then 8. So we get 1248 over 125. So most definitely get your hands off the calculator and spend a bunch of time working with fractions because they're going to come up and you need to know how to do it. Okay, find the infinite sum Sn. So really Sn isn't actually the right thing to write. So we should write just S, no N, because if it's infinite, then there wouldn't be an N there. So the actual sum is, remember, first term over 1 minus R. So literally say first term instead of A1. The first term was 8. 1 minus the ratio, which was 1/5. So we have 8 over 4/5. Flip over your 4/5, and you're going to get 8 times 5/4. 4 goes into 8 twice. 2 times 5 is 10. So this is the answer. And we're not going to do this one because we're not going to find the nth term and do the limit because that's just confusing the way they have this written. So we're not going to do it that way. But we do need to know how to find the sum. Now, so basically what we just found is if you could add up this series all the way to infinity, the actual answer is 10. So it's kind of a bizarre thing. Now, we are very rarely going to ever be able to actually find the sum. Normally what we will be doing from now on is pretty much just saying, there is a sum, but I don't know what it is. I know that it converges to something. I just don't know what that is. We are only going to be able to ever find a sum if it is geometric. Okay, so there's pretty much never any other time we can find the sum, except for one thing I'm going to show you on this video, but then we're not going to have really any questions on it other than homework, because I want you to know it exists, but it's not being tested, and that's called telescoping. So you can also just assume if something says find the sum of the series, then it must be geometric because I don't know how to find it another way. Okay, so let's find each of the following sums. If it's not possible, then we need to explain why. So we can find the sum if it converges, but if it doesn't converge, then there won't be a sum because that means it just keeps getting bigger. So what we need to do is determine what kind of series we have. Well, the only thing we've worked with so far is geometric. So let's see if we can figure out how they're geometric. So on this first one, we can see that it's geometric because 1 over 3 to the n is the same thing as 1/3 to the n. So we're multiplying by 1/3 because you would just do 1 to the n, which is 1 over 3 to the n. This is super important because this is something that a lot of students get confused about and then can't figure out that this is geometric. So 1 over 3 to the n, 1 over 7 to the n, 1 over 2 to the n, all of those things are just geometric. It's really just 1/3 to the n. So that first one definitely converges because r is 1/3 and 1/3 is between 0 and 1. So it will converge. For the second one, I need to look at it a little bit. So even though the top and the bottom superscripts are not the same, like one is n minus 1 and one is n, it's not going to matter. I'm still multiplying the top by 2 and the bottom by 5 every single time. So this is going to have an r of 2/5. So that's still going to be your ratio. So that means that one also converges. So since they both converge, then I can actually find the sum. So it's going to be for the first one. So remember, again, it's first term. So if I plug in 0 for the first term, I'll have 3 to the 0, which is 1. 1 over 1 is 1, times 2 is 2. So the first term is a 2 over 1 minus the ratio, which we said was 1/3. Plus, we know that this one converges, so we just need to figure out the first term. So again, plug 1 in here and plug 1 in there. That's the first term. So we have 2 to the 0, which is 1, over 5 to the first, so we have 1/5. So our very first term is 1/5, and then it's over 1 minus the ratio, which is 2/5. So if you'll think of them that way, then you won't have to get yourself confused if the exponents are one different or anything. The formula is always first term over 1 minus the ratio, okay? So then I just need to do some arithmetic here, which again, make sure you're practicing. So I will have 2 over 1 minus 1/3, which is 3/3 minus 1/3, which is 2 over 2/3, plus 1/5 over 1 minus 2/5, which is 3/5. Now I could have done this a different way by multiplying by the common denominator and simplifying it that way. And I'm going to do that next. So I'm actually going to do both ways so that you make sure that you understand that. So here I'm going to flip over and I'm going to get 6, and I'm going to write this out kind of excruciatingly here. 2 times 3/2, because I'm going to flip it, plus 1/5 times 5/3. So that's going to be 3 plus 1/3, which is 10/3. Now what I could have done that would be much easier, anytime you have fractions inside fractions, you can clear it, and we've talked about this before, by multiplying. So I'm going to take the first one and multiply by the common denominator, which is a 3. So I multiply every term by a 3. So what I actually did was multiply the top of the big fraction by 3 and the bottom of the big fraction by 3. So I just had to distribute on the bottom. So what I end up with is 6 over, this will cancel, so I end up with 3 minus 1, which is 2. So I'll end up with 6 over 2, which is like just what I have there, 6 over 2. So on this one, it would have been even easier. Multiply everybody by 5. And of course, that's in the top because you're multiplying by 5 over 1. Those go away, those go away. That's why we did it. So you end up with 1 over 5 minus 2, which is 1/3, which is the same thing we ended up with. We just would have gotten to those answers quicker. And so I would suggest that that's what you do if you have a couple of those to simplify. Okay, now B, we have to figure out if this is going to converge or not, and then if it does, the sum. Well, the first thing I'm going to have to do is rewrite it a bit because I need this to be terms that look geometric. So I have 4 to the n over 5 to the n minus the sum of 7 to the n over 5 to the n. So I need to split that just like anything else. You can split that because it's a single on the bottom and you have subtraction on the top. So what I really have is, if I want to think of it as geometric, 4/5 to the n minus, and then n equals 0 to infinity of 7/5 to the n. So here we have an r of 4/5, so that's fine, but here we have an r of 7/5. So this diverges, and so I cannot find a sum, okay, because that part diverges. So this is a divergent series, so I cannot find the sum. Okay, properties of infinite series is kind of like when we do limits and we talk about the different cases on whether it's determinate or not. So here, if you have two convergent series, summation of an, summation of b sub n, and then you have capital A, capital B, and little c are all real numbers. So those are the letters we're going to use here. So these are, you got an actual answer somewhere. Then if the sum of the a sub n series is capital A, so I got a number answer of some kind, the sum of the other one is capital B, then the following things converge. So if the sum of the a sub n converges and all I do is multiply by a constant, I'm just going to get the constant times the sum that I would get. So the nice thing about that is if there's a number in front, you can sort of pull it out of the series, get your answer for your summation, and then multiply it back in. This one says if we have both of these that give me an answer, a plus b is going to be the sum, and then a minus b. So you can just subtract them as long as you get answers. Okay, if you get any infinities, it doesn't work that way. Okay, so we're going to talk about telescoping series. This one's just kind of cool because it shows you something and it shows you a pattern and it's kind of neat. But again, it's not tested, so we're not going to have any necessarily test questions over it, but you're going to kind of see it's kind of cool what happens here. So we're going to use partial fractions to find the sum of this series. So this particular series is 1 over n times n plus 1. And so they've just written out for you a couple of terms. So it'd be 1 over 1 times 2 plus 1 over 2 times 3. And you would continue on like that. So in order to get this a little bit better, what we're going to do is we're going to take this and we're going to use partial fractions to turn it into the sum of two different series. And then where we're going to get a sum or a difference here. And you're going to see something cool that it does, okay? And it doesn't work every time, but it does work often, especially when you can write this like as a partial fraction here, you can get something kind of cool. So remember partial fractions, we want to solve this, so we're going to multiply everything by n times n plus 1. So you're going to get 1, and then you're going to get a times n plus 1 plus b times n, and then you're going to let n equal negative 1 to get rid of this term. So you're going to get 1 equals a minus b, so that means b is negative 1, and then you want to let n equals 0 so we can get rid of this term. So we get 1 equals a. So a is 1 and b is negative 1. So what that does is it gives us, for this series, we actually can rewrite it as 1 over n minus 1 over n plus 1, because we know that this is the same as 1 over n minus 1 over n plus 1. Now, let's now write out some terms and see what happens, and this is where it gets kind of cool. So we're going to go ahead and plug in, starting with 1. So if we start with 1, we'll have 1 over 1 minus 1 over 2. And then plus, because this is a summation, 1, and now I plug in 2. So I'll have 1 over 2 minus 1 over 3. And then I'll have plus. And I'm going to put these in parentheses just so you can kind of see what we're talking about here. And I should have written this lower, so I'm going to move it down so that you can see all of this written across better. So let me extend the page. Okay. So then if I do the next term, same thing. I have parentheses around this again just to kind of show the difference. So now I plugged in 1, then I plugged in 2. Now I'm going to plug in 3. So this will be 1/3 minus 1/4. And then if I plug in 4, I'll get 1/4 minus 1/5. And this is going to continue like this forever until you get to the last terms, and the last terms will be, so I have to keep going here, I will have, I'm going to put the last two sets of terms. So the very last set of terms would be 1 over n plus, well, it wouldn't be the last term, yeah. It would be the last terms would be 1 over n plus 1 and 1 over n minus n plus 1. So the term right before that would be 1 over n minus 1 minus 1 over n, because I would just be at the n plus, or the n minus 1 term. So I'd get all of these terms, and then the end would be this. And so what happens is, if we look at this, we can see clearly a pattern. You have a negative 1/2 and a positive 1/2. You have a negative 1/3, positive 1/3, negative 1/4, positive 1/4. So in the middle, all of that will cancel. Something will cancel with that one that was over here somewhere. You'll have minus 1 over n plus 1 over n. So all that you have left in this sum is 1 minus 1 over n plus 1. So all that's left is this first part minus the last part. So that's kind of cool. So then if I want to know what happens as I go to infinity, okay, so if this is going all the way to infinity, I would just need the limit as n goes to infinity of 1 minus 1 over n plus 1, because that's what ended up when I added everything up. And if I go to infinity, then of course I'm just going to get 1. So that means that the sum of this series is 1. Okay, and again, only because it's telescoping is the only way that I'm able to do that. Okay, and so again, we're not going to really do telescoping, so it's just kind of cool to see how it simplifies. Now, it could have been 1 over n minus 1 over n plus 2, and then the way it canceled out would have been different, but still would have had some things to cancel out. So it's just kind of a cool thing to look at, but we're not going to look at it that carefully. Okay, so let's look at that we just looked at, and let's look at the difference between the sequence and the series. So the sequence is just going to be an equals, so I'm going to put it in curly braces, it's 1 over n times n plus 1. So this is going to simply be a list. An is going to be 1/2, 1/6, 1/12, and continues, and it would actually converge to 0, because you can see very easily that the limit of that, if I went to infinity, would be 0. Now, by converging to 0, it means if I just kept writing terms down over and over and over and over and over, I'd keep getting numbers that were closer and closer to 0. The series, however, is the sum of all of those things. Okay, so the series is going to be this, n equals 1 to infinity of 1 over n times n plus 1. And it's going to be 1/2 plus 1/6 plus 1/12 plus and so on, and going to infinity. And we just determined that that answer is actually 1. Okay, so we just determined that by writing it in a different way and looking at something. I would definitely never be able to tell that the sum was 1 looking at the terms written like this. So we had to write them a different way. Okay, so that's just kind of a cool thing, but we won't really test over that. You might have a question or two on homework, but not going to be something we focus on. All right, so we're going to use this to write a geometric series that represents 0.05 repeating as the ratio of two integers. So 0.05 repeating would be 0.050505 ... Okay, well, what that would equal is, right here, if you look at that, that's 5 over 10 squared. And then the next term, the next part you have to add to it would be 5 over 10 to the 4th. And then you'd have to add another 5 over 10 to the 6th, and so on. And that's what the series would look like. And it would continue on forever and ever. And then if we wanted to look at that, we realize, hey, this is geometric. We are starting with a 5 and really 5 over 10 squared, and then every time we're just multiplying by another 10 squared. So the way we could write this if it was geometric is we could say, hey, this is 5 over 10 squared is where we're starting, like that's the first term, times 1 over 10 squared to the end, and that's how I'm going to get to all of my other terms. Well, that means that I know that this is geometric, where the ratio is definitely less than 1. So I know it converges. So that means 0.05 to infinity is going to equal the sum of this series. And the sum of this series is the first term, which is 5 over 10 squared, over 1 minus the ratio, which is 1 over 10 squared. So again, you can simplify this in a number of ways. It's not that big of a deal here because we just have 5 over 100 over 99 over 100. So we can see that's 5 over 99. And then if you do 5 over 99 in your calculator, you'll see 0.05, 0.05, 0.05, 0.05, etc. Okay. So now one of the most important series that we're going to test that we're going to have that actually tests for divergence. The nice thing about this test is if I have this test work, then it means it diverges and I'm done. There's nothing else to do. I've already determined it. So the key to this is some logic that you need to really pay attention to. If a series has any chance to converge, its nth term must have a limit of 0. That's what this says, okay? If a series converges, then it must be true that the limit of the a sub n has to be going to 0, and that should make sense to you. If I'm going to add an infinite set of numbers up, then it better be, as I get to the end of that list, I'm starting to get smaller and smaller and smaller, and I'm approaching 0. Well, the contrapositive of a statement is also true. It's logically equivalent. So this is an if-then statement. The contrapositive is if not, what was the then part, then not the beginning, okay? So if the limit is not 0, then the series must diverge, okay? So this is a big one that I would strongly suggest you highlight. This is the first test that we're going to do on every single problem. Because if we look at the limit of the a sub n term and it diverges, or the limit's not 0, the problem diverges and I'm done. There's nothing else to do. So know the name of the test. There's going to be a lot of them, so you need to start learning them. So this is called the Nth Term Test for Divergence. The key to this is knowing that it's called a test for divergence. It cannot prove that something converges. It can simply tell you that it diverges, and then I'm done, and then otherwise it might converge or it might diverge. Okay, so if the limit is 0, I don't know anything. Okay, so on these next examples, that's what we're going to do. We're either going to get that it converges, or all we're going to get is either it diverges or we're not going to be able to tell. Okay, so the first test you're going to do on every series is you are immediately going to do the limit of the nth term. Okay, now later we won't write them out, we'll just do them in our head because very often they're just 0, so the test doesn't tell us anything, so we don't need to write it down. But we should always check it because nothing is more frustrating than when you learn all these tests later and you spend all this time and realize, oh, I should have known immediately. Okay, so when we do this limit, remember we look at this, we get a limit that equals 1/5. That is not 0. Therefore, this series, and this is how you should write everything and get in this habit, because then I've given my reason, I've given why and everything. Okay, so I simply take the limit, I get a 5th, which is not 0. So make sure you say that because that's the criteria. Therefore, and then write the entire original series down, diverges by the nth term divergence test. and you need to write the name of the test every single time that you decide, because that's your justification, okay? So we don't just say it diverges, we're going to say it diverges by the nth term divergence test. So every time. Okay, next question. So on this one, again, first thing we would do is we would do the limit as n goes to infinity of n over n cubed plus 1. That limit is 0. Well, guess what? We don't know anything, because the limit being 0 is necessary for it to converge, but it doesn't mean that it converges. So the test is inconclusive, or you can just say that we're unable to determine, something like that. So the test, let's just say unable to determine convergence by the nth term divergence test. Now, it doesn't mean we can't determine convergence by some other things, but you don't know how to do those yet. So right now we're just saying, did we learn anything by the nth term test? We didn't learn anything because the limit was 0. Here, the limit as n goes to infinity is also 0, so ditto for the answer. We can't determine anything. Now, I will tell you that B, in fact, does converge and C does not converge. But we don't know that yet. We don't know how to do it. We need more information. We don't know enough. So this test just was inconclusive, okay, the nth term test. So the tests that we're going to learn later in other sections would be able to help us figure that out, okay? And then that's how I know that those do what they do. Okay, so we're going to look at the nth partial sum here and try to write a rule for a sub n. So we're going to use the partial sum formula to figure out what we might have. So basically a1 plus a2 plus a3 plus and so on up to the an minus 1 an. This is going to be the whole thing is the s sub n. If I add up all the way to the nth term, so say it's the 12th term, okay? So I add up the first 12 things, that's the 12th partial sum. So Sn minus 1 is going to be if I stop one short of that, okay? So what we're going to look at is then that means that if we took Sn and we subtract Sn minus 1, we see that what's left is just going to be your An. So if we could write down the formula for each of those and subtract, then we should be able to get our generic term. Or we can get our sums, whichever way you want to look at it. So our nth partial sum has a formula. So we just want to do Sn. So looking at our formula, Sn is n plus 2 over n plus 5. Sn minus 1 means you're going to put n minus 1 plus 2 over n minus 1 plus 5. And then when we simplify all of this, we're going to get a formula for An, because that's what it says. It says this equals A sub n. So we do want to simplify it a bit and see if we can write it a little bit nicer to give us a more succinct formula. So I'm just going to combine this a little bit. So this is still n plus 2 over n plus 5. But on this one, I would combine that as n plus 1 over n plus 4. And then I can get a common denominator. And so it's going to be n plus 4 times n plus 5. So you're going to have n plus 4 times n, or n plus 5 times n plus 4. So this one's also n plus 5 times n plus 4, which we can see then what's missing is n plus 4. So then you need to write n plus 4 here. This one will be missing n plus 5. So write it in both places. And then I'm going to go ahead and distribute because I know that's what I'm going to need to do because I'm going to subtract in a second. So on the top, I'll get n squared plus, that's hard to read, that's a 4. So I'll have 4 plus 2, that's 6n, plus 2 times 4 is 8. And then this one will be n squared plus 6n plus 5. And then I'm going to just go ahead and add my like terms together or subtract. So be careful when you subtract. Everybody gets subtracted, okay? So be careful. And then all of that will be over n plus 5 times n plus 4. So in the top, I'll have n squared minus n squared. That goes away. 6n minus 6n. That goes away. 8 minus 5 is 3. So this is going to equal my a sub n term, okay? So that's just a little algebra stuff that we could possibly do if we were given a formula. And that's what the last example does, and we'll just do that in class as kind of a wrap up, and then you'll be able to work on your homework.